Thank you very much. So I'm going to tell you a little bit about this library we built. So one of the things we do in our group is lots of tool building and to support our research. And so we are building lots of libraries, lots of tools of various kinds, and this is one of the more recent ones. I'll give you some links and things to it and other ones at the end. So just to motivate the reason we have this, I don't know how many people here are into program verification and SMT solving and all that sort of stuff, some of you probably. So we're building a verification tool called Skink, which is basically at the moment targeting verification of C programs, in the sense that we take programs like these and we're interested in automatically verifying whether assertions in these programs could ever fail. Okay, and we're not interested in manual proving or anything. We're interested in an automatic technique that can either say yes, a program is correct because an assertion will never fail, or if the tool can show that an assertion would fail, we're interested in knowing why. So a path in the program and values of variables and things like that. So in these two programs here, the program on the left, if you have a quick look, is fairly obviously okay because the assertion inside the loop is guarded by the same condition on the loop, and the assertion at the end is essentially the exit condition of the loop. So we can probably be happy about that one. The program on the right is pretty obviously incorrect in some cases. Well, in this case, the variable values are given. But in the general case, for example, in the left program, we don't know what the value of R is, so we've got to verify for any value of R. But the program on the right will fail because the assertion inside the assertion at the end will fail. Okay, so this is typically what we're trying to do. Obviously, we're doing it for much more complicated programs than this, and the hard part, as it is in a lot of program verification things, is loops and detecting, working out loop invariants and all that sort of stuff is a whole can of worms. I'm not talking about that today. What I'm talking about today is sort of some of the infrastructure we use to check these sorts of things. So let's look at a slightly more complicated example. So this is a loop that counts down from some number n, could be anything, and counts up at the same time in another variable, and the assertion says that at the end y is not equal to n. So this program's going to be incorrect. But if we're talking about how we might verify this program, the method that Skink uses, it's not original to us, is to basically consider program traces. So think of it as a path through the control flow of the program that leads to a failure happening. Okay, so what we do essentially is we compute the paths, the traces, that are feasible are reachable according to the control flow, and then we use SMT solvers to check whether those paths are feasible or not. Right, and that's the topic of today. So in this case, we could say the first question we might be interested in asking is, could this program fail without doing the loop at all? Okay, and we can represent that by this formula, or this predicate, which basically says that the initial value of x is the same as the initial value of n. The initial value of y is 0. We know that the initial value of x must be less than or equal to 0 because we're not going into the loop, and the assertion, the negation of the assertion, in other words, when it goes wrong, is that the initial value of y is equal to the initial value of n. Okay, and we can do this for any possible traces. So for example, you get this more complicated formula if you assume that you go into the loop once but not twice, and so on and so forth. So there are technical details about how to deal with that. How do you deal with arbitrary numbers of iterations and all that sort of stuff? That's not relevant. But what we're interested in, and what SMT solvers give us, is the ability to take these formulae and ask, is there some assignment of values to these variables that would make this formula true? And if it, in this case, if we get one of those, that means we know we have a failure trace of the program that could actually happen in an execution. So that's a long way of motivating the existence of this library. There are lots of SMT solvers around. Z3 is probably the most famous one, but there are many of them. And one of the sort of motivations for having this library was that we wanted to be able to have Skink utilize many different solvers depending on the circumstances, and it depends a bit on what you're trying to check. So in this case we're dealing with sort of simple linear integer arithmetic, so it's most of the solvers can do that and pretty well, but when you get into trickier cases like floating point arithmetic, non-linear arithmetic, bit vector type things, so if you're interested in computations where you're completely accurate to the bits in some number, or integer or floating point, there are solvers that can do that. Some can, some can't. So one of the things we wanted to do was to isolate the tool as much as possible from the details of all those solvers, right, and be able to replace them, use different ones at different times and so on. So we came up with this library to do this. And it's based on this thing called SMT-lib, which is a standard, if you like, specification of SMT solvers in some sense. So it specifies things like the logics that SMT solvers can support. So if you want to know what really is involved in the linear integer arithmetic logic, the SMT-lib will tell you what's in there, what operations exist, and so on. It also specifies languages for input, in other words, how to send problems to a solver that supports this standard, and how to understand the responses that come back. And you can see an example on the left. So this is essentially that first formula from the previous slide encoded in SMT-lib syntax. It's basically an S expression, Lisp sort of syntax. And you can also do things like at the bottom here, you'll see a checksat command, which basically says, try to find an assignment of values for this formula, and it will say sat, because there is one. And then you can ask, at the bottom there, you can ask for the values of particular variables, for example. So in this case, we can say, what's the value of n at 1, and it will say 0. And if you go back to that previous formula, you'll see that assigning that variable to 0 will make the whole thing true. So that's a failure mode. So this is all really good. Lots of solvers support this standard to varying degrees. It's maybe not quite as enforced as one would like, so some solvers deviate from it a bit, or don't support all of it, or add new things and maybe incompatibly add them compared to other solvers. So there's some variance, and that's another reason why we wanted another layer on top of the solvers. There are a few libraries, or there were a few libraries that did this for Scala already. I just listed a few there. There are URLs for these in the paper. But generally speaking, they didn't do all the things that we thought we needed to be doing. And one is the syntax of this language, this S expression sort of thing, is sort of easy to get wrong a lot of the time because it's not very familiar to people. So if you're writing these things by hand, it's a bit tedious. But also if you're writing another tool, so in our case Skink has to be able to write these formulae out and send them to a solver and get responses back. Dealing with the S expression syntax in Scala is tedious. You'll notice from the left-hand side here that these declarations, these declare fun commands, have to be there because they sort of tell the solver what type things are. So these are scalars, but they're still functions in the SMT solver world. And you have to have those. But you don't find out that you've forgotten one until you actually try and use a variable later on that doesn't have a declaration. So there's a requirement for this declaration before usage, which can be easy to get wrong as well. It's all dynamically typed in the sense that by the time we send that assertion, which might be much more complicated than that one, we might be using the wrong operation on one of our variables for the type we've declared it to be. And again, you don't find that out until you send the assertion, and then everything just crashes. And finally, in a particular verification process, you might be starting, doing lots of solver executions, starting different solvers, killing them off, and so on. So there's a process management aspect, resource management aspect there. So our experience with these other libraries was that they did some of these things, but not all of them, and so on. And most of them were targeting basically one target solver, not supporting lots of solvers. So let me show you what this looks like, and I'm going to try and do a demo with one hand. So hopefully that's readable at the back there. So what I'm showing you is just a few little examples of how to use this sort of thing. So one possibility is you can just do something like take a theory off the shelf. So this is QFLIA, which is linear integer arithmetic. And you can say, I want to start a solver. In this case, we're going to start Z3, and I can create some variables. And then I can do, with the little vertical bar equals thing, I can do assertions basically using those variables. And this is the same formula as the no-loop iteration formula that we saw before. And the advantage from a understandability point of view is that there's kind of a DSL of overloaded Scala operators that map down into the SMT operators. So you don't have to write S expressions. And a lot of the stuff that you would sort of hope to happen is happening here. So for example, we have to say what the types of the variables are, in this case ints, but the forcing the declarations to be output is automatic from the library in the background. Okay, so I can do this, and I can run checksat here to see what happens, and if it works, I can use get value to get the value. So in this case, we can run this, and it says down the bottom, it says sat, and it says that n is 0. So this is sort of the simplest mode of usage. The second example illustrates a slightly more complicated mode, which, so I didn't really emphasize that, but the last thing you have to do here is destroy the solver. Otherwise, you end up filling your machine up with Z3 processes. And so the library has a higher level interface with this using primitive, which essentially is doing the resource management for you. So it's creating the solver that you specify there, making it available to the operations in the body of the using, and then automatically killing it off again when everything's done. Okay, so it's essentially a scoping mechanism, so you don't have to worry about things. So this is a more complicated example. So here we're saying x plus 1 is less than or equal to y, and y mod 4 is 3, and y is greater than or equal to 2, and showing a bit more of the boilerplate here. So this basically returns a try, which you can then pattern match on and do things like get the model and so on. So in this case, let's try that. So we can see that we've got, it's found that x can be 2 and y can be 3 to satisfy those two assertions. And because of the using, the solvers come into existence, being used, and then gone away automatically for us. All right, let's see. I'll do one more. So this one uses real numbers. So 2 real numbers here, and just to show that we're cool, we're using a monadic version of it this time because everybody loves monads. So this sort of stuff can be chained together. I could probably write it as a nice 4 comprehension or something. But the computation here is, b cubed plus b times c is 3. And again, we're doing a checksat and a get model, and then printing out the values. And they look funny because the SMT solver sort of standard representation is as a fractional representation rather than a floating point representation. So hopefully you can check that in your head that those are the right numbers to make this fail. But hopefully you get the idea. So there's this, you can see here, this is NRA, which is nonlinear real arithmetic. So you can switch from the different logics very easily. You can pick the different solvers. I've just used Z3 here, but there's a whole bunch that would be supported. There's a configuration file which lets you add more. So if it's one we don't know about, you can still add it to the library without too much trouble. All right, so let's, to finish up, I just want to say a bit about what this is all built on. So last year at this symposium, we gave a talk about this thing called SBT-RATS, which is a parser generator that we built based on parsing expression grammars. Kayama is a language processing library that we've been working on for quite a long time. So one of the reasons for using this stuff is that we can make the communication between the Scala side and the solver side essentially as easy as pretty printing trees and parsing responses back into trees. And they're all specified by the SBT-RATS grammars, pretty much. And compared to at least one of those other libraries that we looked at had thousands of lines of code to do that. And we have a few hundred lines of grammar, essentially. To manage the communication, we have I don't know how many people know expect. So expect is a old school thing that was written, I think, originally for the TCL language, years ago. It's basically a way of sending stuff to subprocessors and parsing the input that comes back and watching for patterns and doing timeouts and all that sort of stuff. So Frank wrote an expect version for Scala, which is doing all this management of the interface. And we're using the widely known resource management library for Scala to actually do the underlying management. So it's essentially a pretty simple structure. We're building these trees that represent queries that we want to run, sending them to some solver process and parsing the results back to get the information we need. So I might stop there. Frank Cassay actually did almost all the work on this, so he couldn't be here. If you're interested, you can get the whole thing at the first link there. If you're interested in the expect for Scala, you can get that at the second one. And the third link there is an overview of the verification work we're doing. And I'm more on the programming software language engineering side, so you can read about SBT-RATS and Kayama at those sites. But I might stop there, if that's all right. Thank you. Yeah. Hello.
What's the point of an assertion that can never fail?
What's the point of it? What's the point of an assertion that can never fail? So in the, I mean, you mean in the programs that I'm showing you here?
Yeah, those were obviously contrived, but
yeah.
Is there a point to have an assertion that will never fail?
Well, so I think you probably think of it two ways. One is you put assertions in usually on the basis of the fact that you don't think they're going to fail, right? Because you're saying at this point, I'm pretty sure this is true, but you really want to know if they do actually fail at some point in some execution, right? So that's usually the sort of motivation for having assertions, is they're expressing some property that you think is true, but you don't want to just assume it's true. You want to know if it fails sometime. Right? Now, in the context of this, I should say the the reason we have programs in this form is because we're using this tool for the International Software Verification Competition, and that's the form in which the does a program work or not statement is formulated in those. So they're not necessarily all realistic assertions that would be in real programs necessarily. All right.
Okay, thanks.
Okay.
Thanks for the talk. Okay. So my question is, what's your take on error messages? So, I mean, SMT solver basically gives you some values, but is it useful to the user somehow try to explain why did this happen and how can he fix it?
Yeah, so I haven't talked about that here, but one of the outputs of this sort of process is usually some sort of witness that expresses the path through the program to where the failure is. And that witness can be, you know, it goes here and then it goes here and then it goes here and that sort of thing, so through the control flow. And it can also be, you know, at this point where we had n, which we don't know what n's value is, assume it's 17, then something bad happens. So you can actually get, that's why you want to get the values. So this is sort of at the lower level. So the output would be usually a concrete witness that shows this sort of thing. The competition requires tools to produce witnesses, and then the witnesses get checked to make sure they are actually valid failure modes, for example. Okay. Great. Yep. Okay.
Yeah. Thanks.
Behind you. Behind you.
So you mentioned that you kind of wanted the ability to target multiple SMT solvers.
Yeah.
I've played around with these systems myself for some stuff, so I know they could be kind of fuxy. Are there like stuff you've kind of just learned heuristically? Some solvers do certain problems better than others, or do you even like try them on multiple solvers? I'm just curious how you've decided what.
Yeah. So at the moment, what we're doing is pretty much using a fixed solver for different categories of problems. So some solvers are better at real arithmetic than they are at linear arithmetic or something like that. So my colleague Frank, who's done most of this work, is a program verification guy. So he knows the literature, which solvers have said, oh, we have this great new way of doing nonlinear real arithmetic or something. So he knows that's the right solver to use for that purpose. We are planning to implement sort of fallback mechanisms. So try a solver, and if it doesn't work, try another one, and you know, move through patterns, that sort of stuff. But it is heuristic, I think, pretty much.
And is there anything in terms of just to understand the sophistication of the analysis you're doing, where you might like see a problem and like decompose it, where like part of it you send to one solver and like another part you send to another and try to combine the results, like a super solver?
Yeah, that's an interesting idea. We don't do that at the moment.
Okay.
But we haven't got to that point, no.
But that's like one of the future plans you guys have?
Yeah, so I mean, the stuff that I haven't talked about here that's hard is the loop invariant detection. So if you've got loops, it's quite often the case that you don't really want to check no iterations, one iteration, 2, 3, 4, 7 million. You don't want to check all those one by one, right? So what you want to be able to do is find an invariant that invalidates any number of iterations, and that's the hard part. Right? So we have people working on that too.
Okay, I have two questions. So one is performance an issue? So does it happen that you have to send large sets of constraints to the SMT solver or get large counterexamples back?
Yeah.
And you're going through this DSL and then the parsing and serialization and all that. So does that come up or?
Certainly it's not the most efficient way to do it, I would say. For the sorts of things that we're doing, it's not typically a limiting factor. The factor is usually that you just can't solve the problem, you know, with the invariants that you don't have, for example. So the the biggest programs we're doing are sometimes programs with traces that are hundreds of steps long. So there's going to be, formulae expressing the whole effect of those traces. So they're quite big. But the solvers themselves are very efficient at a lot of these different theories, so they're not too bad. One future work thing is some of the solvers have APIs, so you can do in-memory access rather than serialization and everything. So we're planning to add that sort of behind the scenes as well. So Z3, for example, you can run via a Java API. So we'll do that as well. But we haven't needed to do that yet.
Okay.
Okay.
So that kind of leads into my second question,
Okay.
which is, so sometimes when you use an SMT solver, you want to use it sort of interactively or incrementally, in the sense that you give it some constraints and you get a result, and you want to use that result to change or add new constraints. Is that a kind of mode of operation that you...
Yeah, so the examples I've shown you here are mostly sort of send everything at once and get a big result. There is a mode of sort of sending an assertion. I mean, you can check a problem at any time. So you can send a bunch of assertions, check it. If that didn't work, send some more assertions to add to that collection. And there's also a way of managing the stack of assertions. So the SMT lib has a stack sort of model. So you can send some more, but then pop those off and then send some more. So there's the library has support for that as well. Yeah.
Okay.
There's an example in the paper of that. Okay, thank you.
Hi, yeah. So there are now these intermediate verification languages like Boogie out of Microsoft, or Viper, which is based on Boogie. Do you have any thoughts on targeting these intermediate verification languages versus doing the verification constraint generation yourself?
So yeah, we know about those sorts of things. They tend to be at a higher level, or much higher level than what we need for this sort of problem. I didn't really say anything about it, but we actually don't verify at the C level. We verify at the LLVM level. So the variables we're talking about here are LLVM variables and that sort of stuff. So we're trying to take the high-level language out of the picture as much as we possibly can. So I think with the Boogie, Boogie I think gets mapped down to Z3 probably as what already anyway. So we're dealing at a lower level, I guess, is probably the thing.
Thank you.
Okay, thanks.
Okay, let's thank our speaker again.
All right, thank you.